All right, folks, here we go. So you've got 18 and 20 that were highly requested, and then maybe on the number 6. That's another one. So 18 has 2 balls of clay that were thrown in such a way they stick together. What type of collision would that be? Inelastic. The first ball has a mass of this, and is moving in this direction, and so on and so forth. And then once together, they move in the x direction. So, conservation of momentum here, right? That's our key concept. I pulled up a vector diagram sheet just because I'm going to have some things to say, but I'm also going to have a lot of drawing to do. So I thought the grid would help me. So I'm going to start off with that things like, this is number 18, all right, over here, So momentum is conserved both x and y. Inelastic collision. So now, I think after, there's a couple other things I get to put in there. Remember, if this problem doesn't interest you, can you work on your other problems?
Yes.
Yes. So it'd be good. I think I am going to need a vector diagram right at the beginning. So I've got the first ball. We'll call that ball number 1. Has this mass and is moving at 10.4 degrees as measured counterclockwise from the x direction. So that'd be something like this. And that's 10.4. Right, that's what this is, 10.4, yeah. Right? That's momentum number 1. Then the second momentum is 41 degrees as measured clockwise from the x-axis. So clockwise from the x-axis. So, and this is 41 degrees, and this is momentum 2, and then momentum 1, 2 would be in that direction. Right? Now, I could just do vector addition and add the first 2 together, and I'd end up with the third vector. It's going to be a non-right triangle, so I'm going to have to use more trig, law of sines, law of cosines, but I can figure everything out. My other option would be to use components, so I only have to deal with right triangles. So, which way would the class prefer? Components? Okay. You got it. So I'm going to have an x component and a y component. Let's see, P1 cosine 10.4, P1 sine 10.4, and then I'll have an x component and a y component, P2 sine 41, P2 cosine 41 degrees. One of the things also to be careful of in your calculator that you make sure you're in degrees, not radians, right? Otherwise you get really wacky answers. So, momentum is conserved in both the x and the y direction. Wonder what they want me to find. speed of the first ball of clay before the collision. So that would be, let's see, that would be V1. And speed of the combined balls of clay after the collision. So that would be V12. Alright, so let's see, need a physics equation. There we are. And I could even put that momentum 1 plus momentum 2 equals momentum 1, 2. Vectorially. Alright? Good. So let's deal with the y direction first. So we're working off the premise that if I add up 1 in the y plus 2 in the y, I'm going to end up with P12 in the y direction. Right? Concentration of momentum. All right. So, P1 in the y direction is P1 sine 10.4 degrees. P2 in the y direction is negative P2 sine 41 degrees. P12 in the y direction is 0. So M1 V1 sine 10.4 degrees minus M2 V2 sine 41 degrees. Oh, let's just say those two are equal. Oh, I know M1. I don't know V1. I want to know V1. I know M2, and I think I know V2. Right? So at this point, it's just plugging in. Indeed. Nice. So let's see. I'll do my numbers. M1, 1.33 kilograms. V1, sine 10.4. M2, 4.3 kilograms. V2, I think mine was 6.00 meters per second. Sine 41. That's right, right? 6. Yep. Solve for V1. I got, ew, that seems really high. I got a large number, 70.5 meters per second. That seems very high.
Yeah,
So it was correct? Yeah, I kind of want to double check mine so that I don't mess it up twice. How many sig figs they want? Doesn't say. We're getting 3. Yep. Good. So let's keep going. So now I'm going to switch to the, maybe I'll switch to the x direction. And just extend my page. And in the x direction, I have the same idea, P1x plus P2x equals P12x. Right? And so I do, skip a step, M1, V1, cosine 10.4 degrees plus M2, V2, cosine 41 degrees equals M12, V12. And of course, M12 is M1 plus V1, right? M1 plus M2. So this, of course, is M1 plus M2. And then I know everything in there except for V12, which is what I want to find. Thank you, sir. And so, yay! All right. On to number 20. You've got a clothes dryer. Everyone knows what a clothes dryer is, right? If not, learn before you go off to college. It's a good experience. Good. It's a light tip you need. Know how to do laundry. Of this radius and acceleration at the rim, what's the tangential speed? Oh, it has to accelerate because it's moving in a circle. So that's kind of where I would start here. Let's see. So number 20 must accelerate since moving in a circle. The faster and or bigger the radius, more acceleration. Now I could, they don't ask me about the forces, right? So I don't really need a diagram. I might do one just to remind myself that this is a centripetal acceleration. And I know it's just centripetal because they don't tell me that the speed is changing. So the acceleration is just due to the change in direction, which means it must be just centripetal. Remember that perpendicular accelerations change direction, parallel accelerations change speed. So pull out my equation sheet, which tells me that acceleration centripetal is v squared over r, and so they want v, so that's going to be the square root of ACR equals v, and then you're given A, you're given R, you're asked for v. Yay! All right, so the next one that was asked for was number 6. And a racquetball is struck such a way it leaves the racket with speed of this in the horizontal direction. Okay, just so only horizontal. And so as soon as the ball leaves the racket, it becomes a projectile. So that's where I would start here with the ball is a projectile. Projectile. So in free fall. So down at 9.81 meters per second every second. And so here's the ball. Velocity initials in that direction. And it's at some height, and it moves some distance in the x direction. So I'd probably include a little sketch just to remind myself what's going on. All right? So, let's see, what do they want me to find out? Hits horizontal, find the height of the racquetball. Okay. Well, I know that the two dimensions are independent of each other, except for they happen during the same amount of time. That's the only thing they share in common. So whatever amount of time it has to fall down, it has that same amount of time to move out horizontally. So I think I'll start with the horizontal and see if I can find out how much time it has, and that'll tell me how far it fell down, because it takes a certain amount of time to fall down given its initial conditions. So I think I'll start in the x direction and see how that helps me in the y direction. We'll see. So I'm going to start with my basic equation from our equation sheet. There are new copies of the equation sheets in the back if you don't have a up-to-date copy. Now, before I can use that, we need to determine a couple things. Where do you guys want to call the zero position? Where is it? Right here? Okay, so we're going to call right here 0, 0. Which two directions do you guys want to call positive? Up and to the right? Okay. Alrighty. So, horizontally, where I end up, they tell me that 1.96 meters. And that's positive because of how we picked it. I start at 0 meters horizontally. My initial velocity horizontally, remember I'm only dealing with x, is 4.83 meters per second, delta t. Oh, wait a minute, I can forget about that whole part, because I know the only acceleration is vertical, right? Cool. I can find delta t right away. Not even that tricky of math. Someone's looking out for me on a Friday morning. And I get from my projectile to fall 0.405797 seconds. Okay. Well, now let's go to the y direction. I'm actually going to use this exact same equation. And let's see. I'm going to end up at negative h, right? Because if it's h from where it started to the floor, and it's down, it's negative. I start at 0 plus my initial velocity in the y direction. Oh, that's 0, so that whole term goes away, right? Plus 1/2. I'm in free fall, so negative 9.81 meters per second every second for 0.4057 seconds squared, and I get that h equals yay. weird. Most common mistakes will be to forget the 1/2 or forget to square the time. I get 0.808 meters. Well, my h is positive, yeah. But that's just the magnitude of it, right? I took into account the direction by making it -h. So it's good I got a positive magnitude. If I got a negative magnitude, that means I screwed up my direction. So let me see if I got it, 0.808. Yep. All right, so number 12. Swimmer swims in still water with the speed of this. He aims so he can go directly across a river that has a downstream current of this. What must the swimmer's direction be? Oh, so this is a relative motion one. Oh, it's kind of nice. We've had kind of like 4 different ones. A little bit of everything. Good old smorgasbord. Nice. So, for your y, this is what, 12? For your y, it'd be good to have some facts about relative motion, right? And maybe in something about vectors. But I think what we need to crucially get to is the diagram. So I'm going to draw my river this way and say the velocity of the river with respect to the shore is that direction. My swimmer wants to go in this direction, so that's the velocity. The swimmer, I'm going to change it from shore to bank. Sorry if that messes some people up, but I don't want 2 S's. River to bank, swimmer to bank. Everyone knows what a bank is? Yeah, we'll make a little bank here. Right, that you can get that you can get money at.
You know what a river is?
Oh, that's a good question. Does everyone know what a river is?
Oh, it's not. It's surface steps. Oh no, that's also variation.
Yeah, sometimes they block. Yeah, I know what I mean. So so let's see. What we're going to actually have is, guys, velocity of the swimmer with respect to the river plus the velocity of the river with respect to the bank will equal being the velocity of the swimmer with respect to the bank. Right? And so what that looks like drawing-wise is velocity of the swimmer with respect to the river, velocity of the river with respect to the bank, otherwise known as the current, and then this will be the velocity of the swimmer with respect to the bank, and we'll call that angle in there theta. Is that the angle they asked for? Swim us upstream from straight across, so yes, that's the angle they're looking for. Look, that's a right triangle.
Whoa.
What? Let's see which ones we know. So we know the swimmer in still water. That would be the same as the swimmer with respect to the river. We know that one. Oh, we know the current, which is the velocity of the river with respect to the bank. And we want to know that angle. Now we got to pull out the trig, right? What relates the opposite to the hypotenuse? Sine. So sine of theta equals VRB. Notice I've dropped the vectors because it's just magnitudes now. VSR. So I'm going to sine theta equals inverse, or do you guys use the term inverse or arc sine?
Inverse.
Inverse sine. It varies by who you match these roots. Velocity of the river with respect to the bank is otherwise known as the current, 338. And the other one for me is 6.66. And so I can find that angle. And I get 30.5 degrees.
Let's go.
Questions before we jump on to the second part? Joe, do you need a calculator?
Oh, yeah.
You didn't bring one? There's one on the Chromebook, so the calculator, I think. Now they want to know how long is it going to take to get across the river. I really have two choices here. I could figure out at that angle how far he actually tries to swim. Because remember, velocity and displacement are in the same direction. And then figure out, well, at that rate, at 666, how long would it take him to make that trip? I think it'll be easier if I figure out how fast he's going directly across the river, its final velocity, the velocity of the two combined, and get that. And for that, I'm going to use Pythagoras. So I'm going to do that VSR, because that's the hypotenuse squared, equals VRB squared plus VSB squared. And I know this one, that's my 6.66. This one is my 3.38. So, most common mistake will be forgetting the square. Yep. Because people are like, yes, 32.9. Seems a little fast. Oh, I square rooted it. 5.73. That makes more sense. And now I can use that D equals D naught plus V initial delta T plus 1/2 K delta T squared. No acceleration. They give me the width of the river, which is 328 meters. And I get my problem. 57.2 seconds.
I got it.
Yeah, look in it's above the second answer box.